This video is for Kate, and it is the first of a series of 3. Coming next will be Resistance and Ohms law, and to complete the set, components and resistance. But we're starting with the basics: current, voltage and power. Current is the rate of flow of charge. What does that actually mean? In a circuit, the charge that is flowing is negative, because it's electrons that are flowing from ion to ion along the conductor. Let's use a model to help us to try and understand. Here, the bakery at the top is providing bread to the lorries. The lorries drive around the road and drop the bread at the supermarket at the bottom. The lorries return to the bakery for more bread. The bakery represents the cell. The bread represents the energy, and the supermarket represents a component in the circuit like a filament lamp. The lorries represent the electrons, the negative charges. So the current is all to do with how quickly the lorries are going, the rate of flow of electrons. The man here to your right is counting the lorries passing him in a set amount of time. He's measuring the rate of flow of the lorries. So he's measuring the current. Here's an ammeter. Ammeters measure current in amps. 1 amp is a large current, so you often see questions with currents in milliamps. 1 milliamp is 1/1000th of an amp. Ammeters must be connected in series so the electrons flow through them. So current is defined as the rate of flow of charge, and that definition can be represented as an equation, where I is short for current, Q is short for charge, and T is short for time. Remember, current is measured in amps, that's the standard unit with the symbol A. Charge is measured in a unit called the coulomb with the symbol C, and time is measured in seconds with the symbol S. When an aircraft is connected to Earth using a bonding line so that the electrons cannot build up because of the friction when refuelling and cause a spark, that rate of flow of electrons through the bonding line is a current. When an X-ray machine accelerates electrons that have just been thermionically emitted from the cathode across to the anode target, that rate of flow of electrons is an electric current. In a series circuit, there's only one path, so there's only one way the electrons can flow around, and they flow around at the same speed. The same rate of flow of charge is everywhere in the circuit. In a parallel circuit, there is more than one path, and so the current in the main part of the circuit is shared at the branches. So, current is all to do with charges moving, the lorries. Voltage is a measure of the energy transferred, so in our model it's all to do with the bread. The bakery transfers bread to the lorries. Like in a circuit, the cell transfers energy to the electrons. The lorries transfer bread to the supermarket. Just like in a real circuit, the electrons transfer energy to the component, like the filament lamp. Voltage is the energy transferred per unit of charge, or the bread transferred per lorry. Another name for voltage is potential difference, or PD. The potential difference is the difference between the amount of energy each side of a component. This is why we measure voltage using a voltmeter in parallel across a component. We're measuring the amount of energy before and after the component. So it's the amount of energy that's been transferred to the component that we find out, the potential difference or voltage in volts. The definition of voltage can be represented as an equation. The potential difference or voltage in volts is the energy in joules divided by the charge in coulombs. Therefore 1 volt is equivalent to 1 joule per coulomb. 1 volt is small, so you might see in questions kilovolts or even megavolts. 1 kilovolt is 1000 volts. 1 megavolt is 1,000,000 volts. If we go back to that X-ray machine, the large accelerating voltage between the cathode and the anode is transferring lots of energy to those electrons that were thermionically emitted. So they move. They've gained kinetic energy. The equation kinetic energy equals EV allows us to calculate how much kinetic energy they gain. See, it's all linked. The voltage is the energy divided by the charge, so the energy is the voltage times the charge. In other words, the kinetic energy of the electrons is equal to the accelerating voltage times by the charge on the electrons. Let's finish with power. If current is to do with how fast the electron's moving, and voltage is to do with how much energy is being transferred to and from the electrons, then power must be all to do with how quickly the energy is getting transferred. Power is the rate of transferring energy, and it is measured in a unit called the watt. 1 watt is small, so expect to see kilowatts or even megawatts in questions. A kettle is more powerful than a desk lamp because it transfers more energy per second. This means it costs you more to run it if you run it for the same amount of time. Just like the definitions for current and voltage, the power definition can be written as an equation too. Power is energy transferred divided by time. So 1 watt is equivalent to 1 joule per second. But power can also be calculated from another equation by multiplying current and voltage. If we look at Y, current is the rate of flow of charge, charge divided by time. Voltage is the energy transferred per unit of charge, energy divided by charge. So if we times the two together, the charge cancels out, leaving us power is energy divided by time. Power is the rate of transferring energy. I hope the video helped with the basics. I'll be making the Resistance and Ohms law video next, so keep an eye on your notifications because you know that
regular review gets a better grade for you.
Don't forget to
like,
so that I can keep making the videos.
comment,
Especially to request other revision topics.
subscribe.
So you can get notifications of when my next video gets uploaded.